All right, so in this lesson, which is the first of our lessons in Unit 8, which Unit 8 focuses on exponential functions, we are going to talk about graphing, exponential growth functions, as well as being able to identify structure characteristics of an exponential growth graph and key characteristics of the function and its graph. So there is some prior knowledge for exponential functions that you may recall from a couple of years ago. You did learn how to identify whether an exponential function was a growth or a decay situation, which is our part A here. And so what we learned is that this is connected to whether the function is increasing or decreasing. So that's done, increasing, decreasing, remember, is done from left to right. So with this first function, moving left to right, the function is heading down, so it is decreasing. And so that tells us that this function would be exponential decay. Whereas the other function from left to right, it moves upward. So it's an increasing function. And that tells us it would be an exponential growth function. Now, we can also actually tell that from the base value. So in this case, in the growth function, notice the base would be 2. And in a growth function, your base is greater than 1. Whereas in a decay function, the base here is 1/2. In a decay function, your base is less than 1, but still has to be positive. And so we often write that as b is less than 1, but it's also greater than 0. And in the next lesson, we will focus on exponential decay functions. This one, we're going to focus on the growth. The second part here is about the horizontal asymptote that an exponential function will always have. So you'll notice that one end of the curve gets flatter. So the horizontal asymptote is the line that that flat end is approaching. So like here for this end, we can see that the horizontal line the function is approaching is right here. This has a y value of -3. So the horizontal asymptote would be y equals -3. Whereas over on this one, here's our flat end. It's approaching this line, which would be the x-axis. And the x-axis has a y value of 0. So that's y equals 0. There's also a connection between this and the function. So going back to these functions, this -3 is our k value. And notice that corresponds to the number in the asymptote, y equals -3. In the decay function, there's nothing plus or minus after, so that's understood to be a +0. That's the k value there, which corresponds to the number in the horizontal asymptote. So we're going to talk about connections between the function and the graph also for these characteristics, such as what we've talked about here. So we will not be doing context applications today, but we will a little later in this unit. And I just wanted to kind of point out to you, there are a lot of situations that are best modeled by an exponential function, and these are some of them. So many populations, especially growth of bacteria cultures, are best modeled with an exponential function. Evaporation is an exponential model. Loan balance, like when you're paying off your loan, or how your loan balance will decrease as you pay that loan off, is exponential. And, you know, when we take medicine, most medicines, the way the body uses them, they decrease over time at an exponential rate, making it an exponential decay model. And so we'll look at some of those and some other situations later on in our context lessons. All right. This is really, in general, just an exponential function. Could be growth, could be decay. Here is its overall structure that involves our parameters that allow us to identify transformations, which is one way to graph an exponential function and the way that we'll be talking about today. So we have our a parameter, we have our k, we get our h from taking the opposite of what's after the x, and this c right here, that's actually what in other functions has been our 1/b parameter that gives us like a y-axis reflection, a horizontal stretch, or a horizontal compression. Here it's a c because in an exponential function, we use the letter b for the base. And so that base, remember, as I was saying, a base in an exponential function does have to be positive. And it also cannot be the number 1. And that's the reason is because mathematically 1 to any power is still 1. So you don't get a growth or decay situation. If your base is 1, you actually get a horizontal line. It's totally flat. And so it doesn't really apply like other bases would to a growth or decay model. With our exponential growth, remember, our bases will need to be greater than 1. In this lesson, we're going to focus on 2 bases, the base of 2 and the base of 10. But technically, a growth model can have any base as long as it's larger than 1. These we're focusing on 2 and 10 as our bases, primarily because in modeling, they're 2 of the most common bases to use for an exponential model. They're not, you don't have to, but they're common types of models. So we'll focus on those. So now what we want to take a look at is just making sure we all understand that if we're asked to graph an exponential function, what we want to make sure we include. So one thing we want to include is the horizontal asymptote, which, like with rational functions, will be graphed as a dashed line. And another thing, like I pointed out before, the equation of that asymptote, which we'll have to identify separately, is y equals k being our parameter about translations up and down. We will also need to make sure that we graph as many of the key points as possible, which will include transformations of powers of the base. So like if our base is a 2, then we'll be graphing key points that are all powers of 2. If our base is a 10, our key points will come from powers of 10. But in addition to that, we want to make sure that we graph the y-intercept, if it'll fit on our graph, and a 0 when they're reasonable. And we'll always be able to calculate the y-intercept, and we'll make sure, we'll talk about how and make sure everybody remembers that. Zeros, however, right now, our zeros will be either one of our translated points or transformed points from our key points of our base powers, like 2 or 10, or we'll approximate them. But the y-intercept is something that we'll always calculate and should always be able to calculate. The other thing, of course, will be the end behavior. And as you might have noticed with our prior knowledge graphs, we have 2 ends. One end will always kind of flatten out and head towards the horizontal asymptote, and the other end will head either up or down, and we'll talk about that. That will depend on whether or not we have a reflection across the x-axis or not. All right. So this is talking a little bit about one of our parent functions, which is our y or f of x equals 2 to the power of x. So this is for our functions that have a base of 2. And so I just want to point out that really all we're going to worry about here is understanding that the key points come from using some very simple integers from -2 to +3 and plugging those x's into 2 to the power of x to create the powers of 2. Remember that with a negative exponent, such as -2, that doesn't mean negative number. That means reciprocal power. So remember, this would be equal to 1 over 2 squared. That's where the 1/4 is coming from. And to the negative first power would be 1 over 2 to the first power, and that's where the 1/2 is coming from. Then we have, by definition, anything to the power of 0 is 1, and then we have our other powers of 2 here shown also. So these will be key points that we will transform using whatever transformations we identify. All right, so let's take a look at this first problem here. So notice we want to graph the function. We also want to state some of the key features here. And we're going to talk about some of the key features before we graph and do some of the key features before we graph. It is possible to actually do all of these key features without doing a graph, but it takes some experience and understanding of the function itself to be able to do all of them easily. and with confidence. So let's start though with domain. So we want domain range, our y-intercept, horizontal asymptote, which means the equation of, and the end behavior of this function. So let's start with domain. So let's go back again to these graphs we started with in our prior knowledge. So these are both exponential growth and decay. And notice as we move from left to right with the function, there are no breaks in the function, no holes, no vertical asymptotes, no stopping and then starting again. These are what we call continuous functions. Any continuous function has a domain of the set of all real numbers. Let me say that again. Any continuous function, a function without breaks from left to right, has a domain of the set of all real numbers. So our exponential functions, their domain will always be the set of all real numbers because they never have breaks moving left to the right. So that means then that for this problem, I can do my domain without having to graph. So my domain in my set notation would be the set of all x's such that negative infinity is less than x and x is less than infinity. And our interval notation, remember, would use parentheses with the infinities. Now range is a little trickier to do without the graph. So we're going to wait until after we've done the graph to talk about range. Y-intercept, however, is something that you can find not just for these functions, but for any function without its graph. Because the y-intercept, remember, is a point on the y-axis, which means it has an x value of 0. That means that we can calculate any y-intercept for any function by substituting the variable of x with 0 and doing the math. So like here, we would be looking at, well, what is g of 0? Well, that would be 2 to 0 minus 2 plus 1. So then our exponent here would be a negative 2. And remember, this does not mean a negative number. It means a reciprocal power. So this is 1 over 2 squared. That's 1/4. And 1/4 plus 1, when you have a fraction and a whole number, you can they're both the same sign. So here they're both positive. So that just becomes the mixed number, 1 and 1/4. And there's our y-intercept. Horizontal asymptote, we also can and really do need to do before we start the graph. We need to know where this is. Remember, it has an equation of y equals k. So our k in this problem is the +1. So that means our horizontal asymptote must have the equation y equals 1. All right. We're also going to leave end behavior till the end. Once you have an understanding of the functions, it's possible even to know what your end behavior is going to be beforehand without a graph. But when we are first starting, it will be easier to do using the graph and then talk about why it is the way it is. All right, so now we're going to start with our graph. So here, my key points. My base here is a 2. So my key points that I'm going to start with are those points that come from the powers of 2 and using the parent function of y or g of x equals 2 to the x. And remember the x's, we start with -2 and -1, and we go all the way to an x of 3 for these key points. The y's then are taking those x's and plugging them into 2 to the x power. So 2 to the -2nd is 1/4. 2 to the -1st is 1/2. 2 to the 0 power is 1. 2 to the 1st power is 2. 2 squared is 4. And 2 to the 3rd power is 8. These points we are going to transform using the transformations we now identify in our function g of x. Now, remember that this 2 is your base. Your base and your a are separate. Here's your a, here's your base. So don't confuse your 2 with your a. Here in this case, our a value is 1 because this would be like 1 times this power of 2. So we have our k value. We know with our k value that means we're going to go up 1 unit with all of our points. And then the opposite, remember, of that -2 there, that gives us h. So our h is a +2, which means that all of our points are also going to move to the right 2 units. All right, so those are my only transformations that I'm going to do on my key points, up 1 and right 2. So now I'm going to draw my axes in. Remember that I want to kind of keep in mind where my graph is going to be. So I have this horizontal asymptote of y equals 1, and I do not have an x-axis reflection. That tells me all of my points are going to be above y equals 1. So I am going to move my x-axis all the way to the bottom to give me some room there. And then in addition to that, I also know everything is moving right 2 units. So I'm going to move my y-axis to the left some. And so I'm going to, since my x value of -2 is going to move right 2, that's going to put it at 0, which is going to be on the y-axis. So I am going to take a look here. What have I got? Oh, I think this will be good because 3 moving 2 to the right would move to 5. So this gives me plenty of space. So now I'm going to put some numbers. It helps with the accuracy of making sure my eyes put things in the right places. All right, so now I'm going to transform my points. And you can start with whichever point. I like to start with the 3, 8, the one with the bigger numbers, but it's not that big a deal. You can start with the -2, 1/4, whatever you like. So 3, 8. So here's 3, 8. So I'm going to take that 3, 8, and I'm going to move it up 1, right 2. Or I could go right 2 and up 1. It's going to appear at 5,9. 2, 4 is going to move right 2 and up 1. So it's now here at 4, 5. And now I'm at 1, 2. So 1, 2 moves right 2, up 1. 0, 1 moves right 2, up 1. It's at 2, 2. Now I'm at -1, 1/2. It would move right 2 and up 1, which would put it here at 1, 1.5. And then -2, 1/4, which is right about here. Whoops, 1/4 is there. Would move right 2 and up 1. And notice that that's at 0, 1 and 1/4, which corresponds to my calculation for my y-intercept that I did earlier. The other thing you might recall from the graphing instructions, we do have to graph our horizontal asymptote, which is our y equals 1 line. It should be dashed. And here's 1 for y. So that means here's my horizontal asymptote, which corresponds to how my points are curving. They are curving towards that line as they should be. And then I'm going to draw in the function curve. So there's my graph of g of x. So now I finished my graph. I need to go back and finish my remaining key features, one of which is my range. So range, remember, is our y values. So here, what we can see is the y values, all the points of our curve, our exponential growth curve. They're all y values above the y value of the horizontal asymptote, which is a 1. The horizontal asymptote has a y of 1, which means that all the points must have y's bigger because they're above that than 1. And so that tells me my range would be y's that are greater than 1. So my set of all y's such that y is greater than 1. And remember that with interval notation, we go least to greatest. And so that for the y's, that's bottom to top. So we start at the 1 and we go all the way to the top, which is our infinity for y. So 1 comma infinity. We use parentheses because 1 is not included in the range because it's the asymptote number. And the asymptote is not part of the function. That's why it's dashed. So now let's talk a little bit about the range and how you can figure out the range without the graph. You might be interested in that. So my range is y is greater than 1. Notice that 1 is my k value. So my k value is key to knowing my range. But when I know my k value, all I know at that point is my range is either going to be the y values greater than my k of 1 or less than my k of 1. So how do I know which it is, greater or less? Well, that's dependent upon whether or not there is an x-axis reflection in the function. Here, our a is positive, so there's no x-axis reflection. So that tells me the curve is going to be above the asymptote, making my range greater than my k of 1. If there is an x-axis reflection, then my range is going to be the y values less than my k value. So now my end behavior, we have two ends, left end and right end. So with our left end, remember we're heading to the left, so that's as x goes to negative infinity. Now, in every exponential function, one end is going to be heading towards your asymptote, and the other is going to be heading either up or down. So this left end is the end that's heading towards our asymptote, and our asymptote has a y value of 1. That means our y's, which are our function values, g of x, must be getting closer or heading to a y value of 1. They're not going to reach that because it's an asymptote, but they are going to get closer to it. The right end, as we head to the right, we're looking at it as x goes to positive infinity. So that right end is heading up as well as to the right. So that means those y's are getting larger. They're heading to positive infinity. So that right end, g of x, is heading to positive infinity. And that finishes up our key features along with our graph. All right, so for this second example, again, same type of problem, but there's this particular function, this g of x function here, we have to realize this negative right here is not part of what's being raised to the power. If it was a -2, it would be in parentheses like this, and it's not. And if you recall something that I said earlier, exponential functions require the base to be positive. So we're not even allowed to have a negative base value in an exponential function. So there's no way this is what we would be dealing with. So what this actually means over here, this negative, is it's actually your a value of -1. So when you see this negative in front of a 2 to a power, you need to make sure you interpret that as a -1 times a power of 2, like so. That's how it must be interpreted. So here, this -1, that's our a value. And that means that we will have an x-axis reflection in this problem. The +3, remember, it's the opposite of that that gives us our h value. So here our h is a -3. And so that means that we have a translation to the left 3 units. Notice there's nothing after the power of 2, nothing added or subtracted. So that's interpreted as a +0. So that 0 is our k value. So we don't get a translation from that or a transformation from that. But that k is still important for our horizontal asymptote equation here in our key features. So that knowing that k is a 0 tells us our horizontal asymptote has the equation y equals 0. That's also our x-axis. That's also something you should know when you see the equation y equals 0, that corresponds to your x-axis. Now, the other thing that we can do right now, remember, is our domain, because all exponential functions are continuous. All exponential functions have a domain of the set of all real numbers. So our domain is the set of all x's such that -infinity is less than x and x is less than infinity. And then our interval notation with our parentheses. Range, we're going to leave until the end. Y-intercept, however, we're going to do right now, because sometimes your y-intercept might be one of your key points and sometimes it won't. So you need to be able to always be able to do the math to find a y-intercept to make sure that you have it when necessary. So remember, your y-intercept is on the y-axis, so the x number is 0. So we can always calculate a y-intercept by letting x be 0. Now remember, the structure here is a -1 times the power of 2, like so. Oops, that's not right. I don't know where that -1 came from. 0 plus 3. So this power is 2 to the third power, which is 8. And then 8 times -1 gives us a -8 for the y value of the y-intercept. Another reason why we have to make sure we understand that math structure there correctly. Okay, so now I'm going to begin focusing on my graph. So I want those key points. Now remember, my base is 2. So I'm going to start with those points that come from powers of 2. So again, my x's are the nice integers from -2 to 3. And then those are my x's, and my y's are my 2 to the x's. So this is 1/4, 1/2, 1, 2, 4, and 8. And we're going to take these points and we're going to transform them. We have 2 transformations, remember here. We have a y-axis reflection and we have a translation to the left 3 units. Now, that's important since I have to draw my own axes. I know where is it, I have to think about, well, where is it best to draw my axes? Because I have a y-axis reflection, that means all of my points are going to be below my asymptote. Let me say that again. Because there's a y-axis reflection, all of the points are going to be below the horizontal asymptote. And the horizontal asymptote is y equals 0, my x-axis. So all my points are going to be below the x-axis this time. So I'm going to move my x-axis up to the top. I could go here or even one up higher with this graph. Then I have a translation to the left. So that means that my x value of 3 is going to move left 3 to 0. So that means I'm going to move to make sure, and my -2 is going to move left 3 to -5. So if I put my y-axis over here, I should be in pretty good shape. I can get to that -5 that I'm going to need for x. All right, let me put some numbers on here. And this is my negative y portion. All right. So now, unfortunately, for some of you like to be able to start by graphing the starting points and then do all the transformations visually. Unfortunately, our graph isn't big enough to do that and be able to graph what we need to graph. So what I recommend is that you consider what the x-axis reflection does. Remember, what it's going to do is it's going to take all of our starting y's and make them negative. It's going to flip them from positive to negative. So if I look at 3, 8, what's going to happen with 3, 8 is it's going to flip down here to 3, -8, and then it's going to move left 3, 1, 2, 3, and end up here at 0, -8. Notice that corresponds to our y-intercept calculation. That's a good sign. Then I have 2, 4. So 2, 4 flips down to 2, -4, and then moves left. 1, 2, 3. So it's now at -1, -4. 1, 2 flips down to 1, -2, and moves left. 1, 2, 3. 0, 1 flips down to 0, -1, and moves left. 1, 2, 3. -1, 1/2 flips down, moves left. So it's now at -4, -1/2. And then -2, 1/4 flips down and moves left 3. So it's now here. Now, the other thing remember is that we're supposed to graph is our horizontal asymptote. As with rational functions, when you're graphing by hand, if your asymptote is the x-axis, I don't require that you do a dashed line on assignments. Listen carefully. However, with our tests, you will have to show me that dashed line when called for on the x-axis, so it's very clear that I know that you know the x-axis is your asymptote. So it's not a bad habit to just do it now. But if you don't, because it's the asymptote or the axis rather, okay. But on the test, you must do a dashed line for your asymptote, even if it's on the axis. Then I want to, of course, draw my curve. So here I'm towards my asymptote. And whoops, let's try to get that a little better. Like so. So there's our g of x this time. So now I'm going to finish up my key features, the range, and the end behavior. So my range, I can now see my curve. All the y values of the points on my curve are all below my asymptote, which has a y value of 0. That means that my range must be all those y's that are less than that y value 0 for my asymptote. So I've got the set of all y's such that y is less than 0. For your interval notation, remember, least to greatest for the y-axis is bottom to top. So your range in interval notation has to start at the negative infinity and go up to the 0. So from negative infinity to 0. Now, how this connects to your function. Remember that I mentioned your range is going to be either greater than your k or less than your k. So our k was 0. So it makes sense that our range involves that 0. The reason, and then here, once I realized I had an x-axis reflection, that put all of my points below my y equals 0, which gave me a range of y's less than 0. That's how I could do it without the graph. End behavior now. So for the end behavior, we have two ends, left end and right end. Left end, remember, is looking at as x goes to negative infinity. That left end, my function is heading towards my asymptote, and my asymptote has a y value of 0. That means my y's, or my function values of g of x, must be heading towards the value of 0 on that end. Then my right end, which looks at as x goes to positive infinity, this end is heading down as well as to the right. Well, that means that for y, it's heading down to negative infinity. My y is my g of x values. That's my function values. So here g of x is heading to negative infinity. All right, so that finishes up this example. All right, so for our last example, we are going to just look at an exponential growth function that has a base of 10 instead of a base of 2. So with a function like this, we're now looking at powers of 10. So the x's over here, so we're looking at this is our parent. The x's are integers here from negative 2 to 2. And we're looking then at 10 to that x value. So 10 to the negative second would be 1/100th. 10 to the negative first would be 1/10th. 10 to the 0 is, of course, 1, because anything with the 0 power is 1. 10 to the first power would be 10, and then 10 squared, of course, gets us to 100. So with these problems, because our graphing by hand, we're limited usually on the amount of space, we most likely will only be able to use these 3 as our key points. Because 1/100th is super small, very close to 0. So that's hard to graph accurately by hand. And when x is 2, we get a y of 100. That's generally not going to fit onto our graphs at all. So we'll think of these 3, x's of -1, 0, and 1 as our key points to use. And sometimes we'll just use these 2. Sometimes we might just use those 2, depending on what we've got for the size of our graph. Again, being exponential, its domain is going to be the set of all real numbers. It's a continuous function. All exponential functions are continuous. All right, so here's our function with now a base of 10. So I have my key points, which are going to be those powers of 10. So I'm just going to use an x of -1, 0, and 1. So 10 to the negative first power is 1/10. This is coming from 10 to the x. Anything to the 0 power is 1, and 10 to the first power is 10. These will be the key points that I'm going to transform. My k value here is -6. So that gives me a horizontal asymptote like before. Here would be y equals that k of -6. Domain, as I said, it's an exponential function, so it's the set of all real numbers. So our set notation, negative infinity is less than x, and x is less than infinity. Interval notation with parentheses. All right. Y-intercept is found exactly the same way because any y-intercept is a point on the y-axis, so it has an x value of 0. So our y-intercept, g of 0, 10 to the power of 0 plus 1 minus 6. This would be 10 to the first power, which is just 10, and 10 minus 6 gives us 4. So our y-intercept here is 0, 4. Once again, I'll leave range and in behavior until after we've done the graph, but we can use the same strategies as before if we wanted or needed to do them without a graph. All right, let's take a look at our axes. So here there's no x-axis reflection. A is a positive 1, again in this case. And so all of our points will be above our horizontal asymptote. But our horizontal asymptote is down at y equals -6, which means that I need my x-axis to be able to give me space to get down to a y of -6. Then I have here the opposite of that +1. Opposite of that +1 is my h. So my h is -1, which means I'm also going to go to the right along with down 6 for that k of -6. So those are my transformations this time. So where'd my x's go? Uh-oh. All right, let's do that again. So 2, 4, 6. I will put that there. And then since I'm only going right 1 and my x's are going to be pretty small, I'm just going to stick my y-axis towards the middle. If I can get it in the right spot. All right, I'm just going to go with that one. So let's put some numbers on here. All right, this time I'm going to go ahead and I'm just going to graph my asymptote first. It's down here at y equals -6. So I would expect my curve of my key points, which I'm only going to get 3 of them this time, to curve towards this dashed line. So I'm going to start with my 110. Bigger numbers, easier for me to kind of work with at the beginning. So I'm going to move right 1 and down 6. 1, 2, 3, 4, 5, 6. And that puts me right there. Oh no. Did you catch my mistake? It's not to the right, it's to the left. H is negative. Oh no. Left 1. All right, let's fix that. So now 110 will go left 1 and down 6. Now this makes sense. And the reason I caught my mistake is because I knew my y-intercept was supposed to be 0, 4, but I was getting a y value of 4 over here, which that does not make sense. So I was like, what is wrong? And that's what was wrong. Wrong direction on my translation there. So there's 0, 4, my y-intercept, which corresponds to my earlier math. Now 0, 1 is going to move left 1 and down 4. 1, 2, 3, 4. And then I have this -1, 1/10, and it's going to move left 1 and down 4. 1, 2, 3, 4. So it's only getting right here. So what I have going on here then is -2. I'm just checking my math here. All right, so did it again. Counting wrong. I'm supposed to go down 6, right? This is how I caught that things were not working out the way they should, is because these points, I would expect them to be closer to my asymptote as they are in this parent function. See how close they are to the asymptote here? So I'm like, they seem awfully far away. What have I done? And what I did was, for some reason, I only counted down 4 instead of down 6. And I remember saying down 4, which isn't right. So I am looking at, let's go back to my 0, 1 point. So here's 0, 1. It's going to go left 1, now down 6. 1, 2, 3, 4, 5, 6. That is making more sense now. And then I have the negative 1, 1/10, which will move left 1 and down 6. And now it's right above that asymptote. That's what I was expecting. And as you get more experience, those are the types of things that jump out at you more easily to catch your own mistakes. So now I'm going to draw in my curve, which is really steep with a power of 10. Crosses over. Does not look anything like that if you use a graphing calculator. Not so wiggly. All right. So now my range. So remember, for your range, your y values for your range are either going to be y's above or below, greater or less than your k value of -6 here. Here we had no x-axis reflection, so it makes sense that our y values of these points are greater or above the -6. So the set of all y's such that y is greater than -6. And from least to greatest, bottom to top for y, we'd start at -6 and go up to the infinity. So from -6 to infinity. For the end behavior, we have those two ends. And for the two ends, our left end, as x goes to -infinity, that's the end here that's going towards the asymptote. And it's going towards then a y value, function value of that -6. So our g of x goes to -6. Our right end, as it heads to the right, that means x is going to positive infinity. The right end is also heading up, so that means those g of x values are going to positive infinity. Now we've got everything finished and correct. All right, so that does finish up this lesson. I hope you have a wonderful day.